Alright, how's it going? We are coming to the end of things. So next week is partially spent on PA5 presentations, and then like wrap up and discussion of the final and all that sort of stuff. So in some ways this is mostly our last week right here for new material. So I want to talk about PA4, I want to talk about SLPs, I want to go through some PA4 code, we'll go back and revisit tree balancing and talk about some aspects of that, and then we'll talk more about dynamic programming. We'll dig into the Oracle of Bacon a little and talk about breadth-first traversal again, and stuff like that. So any questions before we get started? So let me start with the SLP, because I'm getting lots of questions on that, and it's due in 55 minutes. But is it 5? Okay. Okay.
It says due at 11, but available till 5.
Yeah, it's due at 11, but it'll be available till 5. So that's to get people to try to like get it in before 5. Because if it's due at 5, then I'll get people at 5:30 saying I need another 10 minutes. So, but at 5 o'clock, I'm going to download everything and send it to the printer.
So if we uploaded it like new?
Yeah, that's fine. That's fine. Just make sure it's there by 5, because it actually shuts off for submissions at 5.
Is the submission worth like how much from the grade?
50 points.
Yeah, but like percentage.
I think there's only 100 points, so that's like half of it. Because you didn't do a proposal for this quarter, right? So you've got your upload, and then you got your presentation next Tuesday. So half of that is the upload, half is the presentation. And the SLP, I don't know, is it 10%? 10 of the total grade?
Something like that.
Something like that. So the upload is worth 5 points on your final.
It didn't change anything. I got 50, but it didn't change anything in my grade.
You what?
I got 50, but I didn't change anything in my grade.
Haven't been graded yet.
Maybe it's too small.
I don't know. It depends how you got Canvas set up. But it should be a percentage of your grade.
I felt I still have the same thing.
You got a 0.
It might cut up.
You got a 0?
No, I think I actually graded his already.
No, he graded
I
mine.
mean-
Yeah, you graded mine
No.
too.
No, but I mean, if you got a 0 instead of 50, you graded
Yeah.
now.
I was surprised. Like,
I think it's just because his grade is around the same.
I don't know. Maybe.
Yeah, if it comes out, if it matches your average before that was entered, then you're not going to see a change.
At least not a very big change.
Maybe slightly.
It might be like point something percent. Point zero something percent.
0.001.
Well, test it if it's 0. That'll show you change.
Yeah.
My grade went up to 50. You went up like half a percent or something from there. So I'm not.
Mine, I don't think so. Have percent.
So yeah, upload and presentation. So let me just pop up the announcement. So yeah, your 224 presentation, your 224 poster was basically while you're preparing, you spent fall quarter picking a project, thinking about what you want to do, and that involves things like, digging into a problem area. I want to make a Raspberry Pi based mouse trap. So what does it take to get going on a Raspberry Pi? How can I make something that will close a door to trap a mouse inside, et cetera, et cetera. So you're doing research, you've got a couple of ideas, you talk about those. It's sort of setting the problem space up, right? This quarter, what you've been doing is trying to refine that idea and move towards some kind of, possibly working prototype by the end of June. But part of that is, you're coming up with a design for your solution. So what you're talking about in this poster is sort of the next step of your project. So what have you done since, the December presentation in terms of pinning down the details of the design, starting to do some implementation, things like that. And then in 223, Your final upload is going to be a formal report, okay? That basically spells out everything about your project, all the details about how you implement it, all the schematic diagrams, the code, that kind of stuff, right? And that's potentially a 30, 40 page document, okay? It's a formal presentation of, here's what I did for my, 40 some weeks of working on this project. So this is all kind of like building on each other. So for this one, yeah, it's just another poster, but it shouldn't look exactly like your previous poster, assuming you've made some sort of progress, and it doesn't have to be forward progress, right? Sometimes you start digging into solutions and you're like, well, that's not going to work, and you look at something else and it's like, well, that's not going to work either, and that's progress, right? So even if you don't feel like you're closer to a prototype, right, you're still eliminating possibilities or whatever. So does that make sense? All right, so upload that, we'll have them printed off, and then you can present them next Tuesday. All right, so PA4 is graded. I spent the whole weekend grading PA4. I finished like 7 o'clock last night, so I had a little bit of a weekend. But PA4 looked really good, right? So people seem to have the idea of trees. You seem to have the idea of recursion, basic tree algorithms. How do we inserting things at a leaf, searching, traversal. Everybody pretty much nailed. Again, the real bugaboos are delete and breadth first traversal, just because there's edge cases in delete, and queue handling takes another layer of coding to make that work for traversal. But not a whole lot of things that I saw that I would say, like, we're in big trouble here or something like that. And so I gave you some feedback. If there were issues, I showed you where I took off points. Really common issue was in the delete algorithm. So you may have heard me say this a few times in class. When you want to delete the root node, the algorithm you're required to do is take the largest node from the left subtree and use that to replace the root. Do you remember my saying that? Okay, so, and then I said the one exception is if there is no left subtree, you can't find the largest thing there, and so in that case you're allowed to just move the root to the root of the right subtree. And that's the only exception to our rule of using the largest node from the left. But probably about a quarter of the class did the following. So here, if you want to delete the root, take the largest node in the left, use that to become the new root. That's fine. So according to that algorithm, if you want to delete the root of this tree, take the largest node in the left subtree, that's a 15, that replaces the root. So this should be the tree you end up with. But you may observe that effectively, since there's nothing on the right, we could delete the 20 by simply moving the root down to here and saying there's our new tree. And that does work. That is a way to delete the root of this tree, right? But it's not using the algorithm that we wanted to use, which is take the largest thing from the left subtree and put it on the top. So eventually I just put this text into a file so I could just copy and paste it, because I had to put it in so many people's comments. So if you got a comment saying you're using a delete algorithm that's different from the one we talked about in class, chances are that's what was going on, was you had an extra special case where you said if there's nothing on the right, move the root down. Sometimes it was something else, but if it looked like the result of the delete was different from what I expected, you got that generic comment there. And I can drill through your code with you if you want to see exactly what was going on, but I saw that in at least some of the cases. And that's just, doesn't mean you don't know how to handle trees, you don't know how to write code, you don't know recursion, et cetera, et cetera. It's just a detail on the requirements. Breadth first traversal. So some people just didn't include it, right? If you couldn't get it working, don't include it if it's going to seg fault the code, because then I can't grade anything else. In some cases, it dropped off part of the nodes, and that might be happening if, for example, you were inserting either the left or the right subtree into the queue instead of both. And I saw that happen a few times. And again, that's just, figuring out exactly what the algorithm is asking you to do. The other most common issue that I saw so is this tree balanced? Absolutely not. It's basically two linked lists, right? We've only got 1, 2, 3, 4, 5, 10, 11 nodes. We can store that in just 4 levels instead of 1, 2, 3, 4, 5, 6 levels. This is absolutely not balanced. But the height of this tree and the height of that tree are the same, right? But there's actually 3 things that have to be satisfied for a tree to be balanced. The heights of the subtrees have to be close, and the left subtree has to be balanced, and the right subtree has to be balanced. And if you're writing an isBalanced function that returns a 1 if it's balanced, right, that just goes into your if statement if the absolute value of the difference of the heights is less than or equal to 1, and isBalanced tree left and isBalanced tree right, then the whole thing's balanced. So I took off a few points if you were flagging this as balanced. So those were the most common issues I saw. And like I say, I think everyone's in great shape as far as the course goes and as far as trees and recursion. And we're going to use all this stuff in 223, right? So this stuff will be sort of the backdrop against which we learn object-oriented programming, and we learn Java, and we learn how to make GUIs and stuff. So this is good stuff to have nailed down. So questions on PA4 before we look at some code? Yeah.
Is it when you run your program with Valgrind and then you check it and it says everything's zero, is it still possible to have memory leaks?
It's possible that under different circumstances you could get memory leaks, yeah.
Okay.
Right, so it may be that some test cases free all the memory and some don't.
So you probably should run, not just like open, close it.
Yeah.
Okay, that might be why.
So usually with trees, what I like to do is exit with an empty tree, right? And in some cases that was seg faulting. So you're trying to free too much. So empty with an empty tree before you do anything. Make sure that works. Throw in one node empty, make sure it frees. Throw in a bunch of nodes empty, or exit, make sure it frees everything. And then make a big tree, delete a few nodes, exit, and then make a big tree, delete all the nodes, exit. And I think those probably cover the test cases.
That's probably why I only tested a few things.
Okay. And if you're getting warnings from Valgrind, pay attention to those. And in some cases, I got 250 lines of errors from Valgrind, but at the end it said all blocks freed, no leaks possible. So you got credit for freeing all the memory. But the fact that it's giving you all this backtalk about uninitialized variables and things like that, those are things that you should probably try to clean up, because it tells you that things are working, but that's kind of partially luck, right? It's telling you that things are uninitialized, but it didn't break anything in this case, but on another system it might. And usually that's happening, like if you do malloc to create a new tree node, you got to set the left and right to null if you want them to be null. If you don't explicitly set them to null, they might turn out to be null anyway, because that's what malloc is doing today. But Valgrind is warning you that you're using this value, but you didn't give it a value to begin with. You didn't initialize it. And those are things that can fail sometimes unexpectedly. So Q code first. I haven't looked at this. So this is my PA3 code modified to make a queue of nodes. So first of all, so struct node is a tree node, and I've got uppercase node typed F to a node star. So I can just say uppercase node, and that means a pointer to a tree node. So init_q returns a q node. Add takes a tree node and adds it to a queue. Remove pops the head off of the queue and returns that tree node. Right, so this is just PA3Q code, but instead of integers, it's doing uppercase nodes, pointers to tree nodes. So, for example, my sentinel node, I just made the data null. Since it's a pointer, I made the next null. That's the sentinel. So, for example, removing, if there's nothing in the queue, that's an error. Otherwise, remember where the sentinel is pointing, so that's temp. Take temp's data, save that in a local variable called data, which we're going to return. Have the sentinel point to whatever temp is pointing to, free what the sentinel was pointing to, and then return that node. Right, so that's a pointer to a tree node. And the add code also takes a pointer to a tree node and just jams that into the linked list. So this code's, like I said, it's the same as PA3's code, except where there used to be an int, now there's a struct node star, or an uppercase node. So the tree code, so I used a single piece of code to do traversal, and I just passed it an argument saying what kind of traversal I want to do, so NLR, LNR, or LRN. So those are just magic numbers that are coded and defines. Root equals null, that's the empty tree. You could make an init tree that just returns null. And then kind of our standard input loop, so read a line of input. If it's an integer, saying I want to enter that number, go ahead and search for that in the tree, and if it doesn't return null, then that means the number's already in the tree. Otherwise, go ahead and insert it. And again, every time you call insert, you got to reassign that to your root of the tree. If they're not putting in a number, then they're asking for some kind of command, so I just switch on the first character. So x to exit, or x to display information about the tree, so that's an examine function. Question mark to show valid commands, s to do a search, and again, look for a number with scanf. So this will match an s followed by an integer. If that's not the format, it's a usage error, otherwise call search, etc., etc. D for delete is exactly the same thing. Q to quit, free the memory, and then anything else, give a help message. And at the end of all this, if you hit Control D, just go ahead and call your memory free. So let's leave delete for last. So insert, we saw this code on the worksheets we were doing. If our number lies to the left, insert into the left subtree and replace the left subtree with the result. Same thing for the right. And if the root's null, just create a new node and return that. And you have a tree with a single node in it. And new node just does a malloc, sets the data to whatever value you want, and sets the children to be null. Traverse takes an order, so that's our 1, 2, or 3, right? And then calls lowercase traverse on the root with that order. So lowercase traverse, basically, if the root's null, return. Otherwise, we're going to traverse the left and right trees. We're going to print the data, and they print the data based on what order you want. So if you're asking for NLR, I print the data up here. Traverse the left tree. If you're asking for in order, then I print the data here. Traverse the right subtree, and if you're doing post order, print the data here. And print data just prints a comma before you output if this flag is 0. Otherwise, it clears this flag. So that's just the comma thing. I didn't take off for the commas because I didn't notice them until about halfway through. So examine does the 3 traversals, does a breadth first traversal, prints the height, tells whether the tree is balanced. Search we've talked about, usage is not interesting. Freeing the memory in the tree, so that's post order, as was suggested in class. So release the left subtree, the right subtree, and then release the root by calling free. And that's just a recursive. Free all the stuff. Breadth first traversal, this is the algorithm we've put on paper a few times. If the root's null, there's nothing to do. Otherwise, initialize a queue, and then take the root, add that to the queue. And then here's our main loop. Remove the head of the queue. If it's not null, meaning the queue is not empty, print out a comma if it's not the first node. Print the data, and then insert the left and right subtrees if they're not null. And then at the end, print a new line, and then release the memory in the queue. So it rebuilds the queue each time. Height is recursive, so just 1 plus the maximum height of the left or the right. Balanced, again, find the height of the left and right subtrees, do a homebrew absolute value function. If the difference in height is bigger than 1, it's not balanced. If the left subtree is not balanced or the right subtree is not balanced, then it's not balanced. Otherwise, return a 1, saying it's balanced. So let's look at delete. So if the root's null, don't have to delete anything, just return. All right, if the root of the tree is equal to the thing we're trying to delete, so all of this code is for deleting the root. So if the left subtree does not exist, that's our one exception, right? Set new root equal to the root of the right subtree, free the root, return new root. So that's that one edge case where there was nothing on the left, and we wanted to delete the 20, we just returned the 30. Yeah?
I think the reason that so many people use a different algorithm is because of the different.
At what point?
I don't know, a lot of people I've talked to use the same algorithm as me, it's what I have in my notes.
Yeah, I'm trying to figure out where that came from.
I think you mentioned a different one in class, and people might use some
It's possible. Because I tried to be really dogmatic about, like, the only way that you can receive full credit in your delete is to replace by the largest. But yeah, I'm pretty sure something gave a different impression somewhere. Alright, so if the left tree is null, we move the root down. Otherwise, we go to the root of the left subtree. Okay. And if there's nothing on the right, that's another edge case. So that's where, here's our root, and here's a node, and it might have other stuff here, but this is null. And in that case, this is going to move up to the root. Right, this is the largest thing in the left subtree. So in that case, change that node's right, which is null, to be the right of the entire tree, free the root, return that node as the largest, as the new root. Otherwise, we do a loop, which basically says, well, temp right is pointing to something, move down to that. So temp is now the prior node to the largest. So we're going to make the new root temp arrow right. Temp arrow right adopts that largest value's left child. That largest node adopts the original right subtree on the right, the original left subtree on the left. We free the root, and then we return that largest node. Otherwise, we just do the recursive version. So if you're deleting something smaller than the root, delete from the left subtree and replace the left subtree. Otherwise, delete from the right subtree and replace the right subtree. So questions on that? So, for fun, because I have weird notions of fun, I wrote a version of this that does tree balancing using the AVL code that we talked about. Which I don't think I've coded up since I was an undergrad. But I talk about it in here and I tell you it's a fun algorithm, and I decided I'm going to code this up. So remember, the idea is when you do an insert, you may, in a balanced tree, all your balance factors, right, difference of left minus right height, should be 1, 0, or minus 1. When you do an insert, a balance factor may become 2 or minus 2, in which case your tree is no longer balanced. But if you find the first place where this occurs, you can determine which case you're in, right, one of these 4 cases, and do an appropriate rotation or 2 to bring you into a balanced setup. And when you do this on the board and you insert something at a leaf, you work your way up and calculate balance factors. But it turns out you don't have to actually do that when you write this in code, because of the way that we're doing our insert recursively. We're inserting at a leaf, but that's going to trickle back up, right? When we add something down here, that's going to return to a call made from inside insert, where we were inserting into this tree and then tacking that onto here. So each time that we recursively call our insert function, we can take the value that comes back and just check the balance factor at that node. And if it's 2 or minus 2, we can make our adjustment from that point down. We're going to be sitting either here or one of these. And once we adjust that, the following calls that we recurse back to, the balance factor should be within balance. So all of that is a long-winded preamble to this. So our insert function doesn't have to change a whole lot. If the root's null, we just return a new node, and our entire tree has a single node that's got to be balanced. If we're inserting data to the left, we insert our data into the left subtree, and we replace our left subtree with that. And then I call this function adjust, which says, okay, at this point in the tree, let's check the balance factors. And if our balance factor is off, let's go ahead and do some rotations, and we return the root, and we do the same thing on the right. So tree adjustment code. So calculating the balance factor is easy. If the root's null, the balance factor is 0, because both subtrees have a height of -1. Otherwise, take the height of the left subtree, subtract the height of the right subtree, that's the balance factor. So that's a one-line calculation. So you can pass in any node called root, and it'll return the balance factor. So adjust basically checks as if the root's null. Again, don't have to do any adjustment. If the root has a balance factor of 2 and the left subtree has a balance factor of -1, that's this case over here. Root is 2. We know that the left subtree is going to have a balance factor of either -1 or 0. Right? So if it's 2 and the left is -1, we need to make this left-right adjustment. So I call this left-right and replace the root with that. And what that does is turns you into a left-left case. So now I just fall through into a second conditional. If the balance factor is still 2, then I need to do a left-left adjustment. And if it was left-left to begin with, then this first if statement would not have fired, and I would just do a left-left. And then same thing on the right. -2 and 1 is a right-left, and -2 and not a 1 is a right-right. And then the only thing left to do is to code up these manipulations, and we did this a little bit on the board one day. So what does this look like? So here's our left-right adjustment. So the balance factor of the root is 2, the balance factor of the left child is -1. And as I suggested in class, I just make a bunch of nodes. N5, N4, N3 correspond to these numbered nodes, and then A, B, C, D correspond to the lettered nodes. So I initialize those to null, because I don't know if they're going to exist or not. I set N5 equal to whatever the root node is that we're starting from. I set D equal to N5's right child, and I said node 3 equal to N5's left child. So that's setting up these two nodes. Right, and I'm just naming them basically. And then if N3 is not null, I don't think it can be null, but I didn't want to think too hard about it, so I put an if. If N3 is not null, I set A to the left subchild and N4 to the right subchild. So that's setting up these entries. And then if N4 is not null, I set B to N4's left child and C to N4's right child. So now at this point, all of these variables correspond to these points in my tree. And what I want to do is turn my tree from this upper part to this lower part. So I want to change node 5's left child to be node 4. Its right child will still be D. 4's right child will be C. I want to change 4's left child to be 3. And I want to change 3's right child to be B. And that's what these statements do. And then you return the root of the tree, which is N5. So it's nightmarish code if you make a typo, right? But again, it's really just saying I've got names for all these nodes. I want to change N5 to point to 4 on its left, so N5 arrow left equals N4. I want to have node 3 point to B on the right, so N3 arrow right equals B. And if you write it carefully, it actually works. So the others are just similar versions of this. So the left case is a little simpler because all we're really changing is node 5 left becomes C, right, to pick up that. And node 4 right becomes 5 to make node 4 the root and then return node 4. And then the cases on the right are the same, right, left, and right, right. And then delete also works, although I can't claim 100% that I understand how this works, but I just adjust it everywhere that I change the root. So I'm probably doing too much work, but that works. So what's the moral of the story here? Right, this is meaningless gibberish. Right, very few of us can look at this and understand tree manipulation. And if we don't understand trees to begin with, this is really not going to teach us about trees and about balancing, right? This is write-only code, right? You start with this, and your goal is to turn this into that, and so you kind of close your eyes and you write the code that corresponds to this, and you end up with this. And promise you, no matter how many comments I put in here, if I come back to this in a year, it's really not going to work for me. It's going to be really hard to sort of know, like, if I wanted to change something in here, how to do that. I would delete it and I'd write it again. That's what I mean by write-only code. So this is not like where the information is, right? This is where the information is. The challenge is, given this, can you write that, right? So think about that, and I won't say code it up week 9, but think about how you would write code to do some of these things. I think it's a good exercise to sort of play with. So questions on AVL trees? questions on PA5? Dynamic programming, knapsacks. Yeah,
How do we read the items from a singular folder?
good question. Right, so open your file using an fopen call. So file fp equals fopen, file name, comma, double quote r. And then fgets string, however long your string is, and instead of standard in, use fp. And that'll read up to 128 characters, put it into this character array. And throw this in a while loop while it's not equal to null. So if fget succeeds in reading something and loading it into string, it'll return non-null. So if it returns null, you know that it hit the end of the file. That kicks you out of your loop, and there you can do an fclose on fp. I'll do it in code because it's easier than. Stick to. Yeah.
So whenever you're reading in data from a file and say there's only like 40 words on, or 40 letters on the first line, but you do fget 60, does it read the 40 and then start going to the next line?
No, so it'll stop reading when it gets to a new line.
Okay.
So it's the same thing as when you hit enter, it stops, it comes
If you
back.
get like 20 and then did fgets again, would it start on the next line or would it start?
It'll always start on the next line, yeah.
Okay, so
The only difference is if I tell it to read 128 and there's actually 200 things on there, it'll only read the first 127, and then when I call fgets, it'll continue on that line.
oh yeah, that's what I meant.
Yeah, okay. Right, so open your file with fopen, and then just use that file pointer that you get back in place of standard in fgets, and loop until it returns null. And Alright, so this is junk code you can use to play around with these functions. So let's just initialize a line counter and increment it every time that we read a line. And that should tell us how many lines we had in our input at the end. It's red knapsack.data, and there's 4 lines. Every line ends with a new line. That's a feature of fgets. So if you don't want that, you can remove it. But presumably you would take this string and you would pass it to scanf. And if you scan with a %d, %d, %s, that'll map out into these 3 fields. And just save those in variables. Make sense? Yeah.
Are there any particular edge cases that are easier than this that you think a lot of people run into?
For PA4 in general?
For PA5?
PA5 in general? Yeah, so if I say the bag can hold 10 pounds and all my items weigh more than 10 pounds, then the maximum value I can get is 0. And you shouldn't have to look for that explicitly. It should get picked up by your code. But depending on how you write your code, that can be an edge case. And that's a problem potentially. I would check if your bag holds 10 pounds, make your most valuable item weigh exactly 10 pounds, and that should be the one it picks. So that gets a case where there's a solution that has only 1 item in it, and it's a bit of an edge case. I think those are the main ones. And again, you're totally encouraged to share knapsack.data files with one another. If you've got a input file and a capacity and you're not sure it's doing the right thing, you're totally welcome to share your file with another group and say, hey, can you try your code and see what you get for the max value on this setup? And you should all get the same answer, right? Sometimes the combination of items is ambiguous. It might be 2 pencils or a mouse and a pair of sunglasses have the same value, but the maximum value itself should be the same for everyone if you use the same file and capacity. So swap test cases if you like. Yeah?
So I think I'm just going to this, but we should be that one data files?
So there's a sample one under /temp. There's a knapsack.data, but that's just one sample file, right? And I'm going to test it with multiple knapsack files, so you want to do the same, because sometimes you'll come up with a file and an incorrect algorithm may always get the right answer. For example, if well, yeah, so try different test cases. And again, if you want to talk on Canvas or you want to just talk to people and say, what test cases did you try, right, I'm okay with that, to compare different input files. But there's one under /temp just to get you going on like the format of the file. Sound good? All right, so don't spend too much time on this, but if you can find where I might have said that you can delete on the assignment by moving the root for an empty left tree, let me know. Okay, cool. All right, so I'll probably give points back then. All right, see you next time.